Okay guys, in this video we are going to continue our discussion of thermal energy, and we'll be discussing heat and heat capacity. So heat, and we use the symbol lowercase q here in these notes, heat represents a transfer of thermal energy between two objects that are at different temperatures. So recall that thermal energy is proportional to the kinetic energy of the molecules within an object. And so if you have two objects that are at different temperatures, one has a larger thermal energy than the other, so the molecules within the hot object are moving faster than the molecule, on average, than the molecules in the cold object. And if you bring these two objects into thermal contact, what will happen over time is that thermal energy will leave the hot object and go into be transferred to the cold object. So the molecules of the hot object will slow down and the molecules of the cold object will speed up until they all have roughly the same kinetic energies, and then the same on average, and then the same thermal energy basically throughout the system. Okay, so that's what heat is. It's a transfer of thermal energy between two objects at different temperatures. Different processes can produce energy, and so we classify these as being either exothermic. This is a process where the system produces energy and produces heat. The other way of characterizing a system is as being endothermic, and this would be where a process absorbs heat from its surroundings. And so we've got two graphical examples of this here. Here you see someone is welding together two pieces of metal. There's a chemical reaction going on. The acetylene is essentially being burned in the presence of oxygen. This is a very exothermic reaction. It produces a lot of heat, which is able to melt the welding materials so that you can create a joint between the two pieces of metal. Here in this example, this cartoon example, we have a instant cold pack where you have a bag that's filled with ammonium nitrate. Ammonium nitrate is a soluble ionic compound, and then there's an inner bag of water. And so what you do is you squeeze and pop the inner bag of water, and then the ammonium nitrate will dissolve. And it turns out that the dissolution of ammonium nitrate is an endothermic process. It's going to absorb thermal energy from the surroundings, and it's going to feel cold. The bag will feel cold to the touch. Well, we are going to talk next about a property of matter called its heat capacity. Okay, and so the heat capacity is a proportionality factor between a temperature change and the amount of heat required to create that temperature change. Okay, so formally, the definition of heat capacity, it's the amount of heat that is required to raise the temperature of a substance by 1 degree Kelvin. So let's suppose that a system goes from T1, its initial temperature, to its final temperature. The amount of heat that's required to create that change in temperature is proportional to the heat capacity of the system. In this equation, heat capacity, C, is an extensive property of the system. It has units of joules per Kelvin. So the heat is an energy that has units of joules. We measure our temperatures in units of Kelvin, and so the heat capacity needs to have units of joules per Kelvin in order for this equation to work out. We can convert the extensive version of the heat capacity into an intensive version by dividing by the number of moles of sample that we have. And so here, that's what I'm defining this C subscript M, which stands for the molar heat capacity. You take the heat capacity of the system, divide by the number of moles, and so then you get a quantity that is joules per Kelvin per mole. And then in order to use the molar heat capacity in this equation, what you do is you substitute in for the heat capacity. So we get this modified equation where the heat required to create a delta T depends on the number of moles of the substance that you have and the molar heat capacity of that particular substance. And different substances have different molar heat capacities. In this slide, we're talking about a different version of the heat capacity called the specific heat with the lowercase s. The specific heat is essentially the molar heat capacity of a substance divided by its molar mass. And it's going to have units of joules per Kelvin per gram. And so the specific heat represents the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Kelvin. Just as different substances have different molar heat capacities, they also have different specific heats. The specific heat here is the proportionality factor in this equation, where in order to calculate the amount of heat required to create a certain change in temperature, you need to multiply by the mass of your sample times the specific heat of the sample. And this is the equation that we are going to be using in the upcoming calculations. Okay, so this is the one that you want to commit to memory. And let's see how it works out. So in this problem, we are being asked to calculate the heat that is absorbed when 15 grams of water is raised from 20 degrees Celsius to 50 degrees Celsius. And then we're given the specific heat of water, 4.184 joules per gram per degree Celsius. And so let me show you how this equation works. We take Q equals mass times specific heat times delta T. We've got 15 grams of water. We'll multiply that by the specific heat. And then we're going to multiply that by the temperature change, 50 minus 20 degrees Celsius. Okay, and we'll just, I'll start here with the temperature difference and take 50 minus 30, well, this is 30 degrees is the temperature difference, times the specific heat, times the mass, and I'm getting 1,882. We'll round that up to, let's see, I guess we should round that just to, well, we'll write 2.8 joules. And then I'm going to correct for the sig figs. This will be 1.88 kilojoules. It should have 3 sig figs. Notice the units canceled out, the grams cancel, the degrees Celsius cancel, so our answer is in units of joules. Let's see. So here we have iron metal. It has a specific heat of 0.449 joules per gram per degree Celsius. How much heat is transferred to 5 grams of iron that's initially at 20 degrees Celsius when it's placed in a pot of boiling water? Assume that the water is at 100 degrees Celsius and that the water remains at this temperature. And then the second question, which we actually need to answer first, what is the final temperature of the iron? Well, if you place the iron in the boiling water and you keep the boiling water at 100 degrees Celsius, then the final temperature of the iron will also be 100 degrees Celsius. And then to calculate the heat involved, we just use the specific heat formula again. This time we've got 5 grams of iron, multiply by that specific heat for iron, and then the temperature difference here is going to be 100 minus 20 degrees Celsius. So we've got an 80 degree temperature difference times the specific heat. I'm getting 180 point joules out of that calculation. Okay. Let's see. Here are just some different variants of the same equation. So here we have an unknown piece of metal that weighs 348 grams. When the metal absorbs 6.64 kilojoules of heat, it's found that its temperature increases from 22.4 to 43.6 degrees Celsius. Calculate the specific heat. What we need to do is to rearrange the specific heat formula. So we'll have Q over M delta T. The heat was 6.64 times 10 to the 3 joules. The mass, 348 grams. And then the temperature difference, 43.6 minus 22.4 degrees Celsius. And so now we'll calculate the specific heat in this way. And I'm getting, at least out of my first calculation here, 0.900 joules per gram per degree Celsius. I just want to check that really quick. Yeah, so I got the same number twice, so let's keep that as the answer. The follow-up question, part B, is identical to the one that we've just done. You just need to change the numbers, but the formula that you use is the same. So let's see what we have next here. Well, I guess that's the last example we're going to do in this video. In the next video, we'll work with the specific heat formula a bit more as we study the technique of calorimetry.